about weather at BTV, and it's more temp. So that's all really what you have. So what's one thing? Be as specific as you can be. Shock.
I did my every 10 years, and my graph looks like a line graph.
Cool. That's a nice conclusion. I like that. Something else specific. You all looked at the same data set, so we should have some conclusions out there. Anybody? Yeah. Yeah.
Maybe we just said 1884 to 1920. There's this very slow decline in average annual temperatures.
There is a very slow decline in average annual temperatures. I like that. Very specific. Good. Okay. Something else. Yeah.
There was a cold spell from 1960s to 1980s.
From the 1960s to the 1980s. What do you mean by that?
The temperatures dropped from that expecting time.
Seem to drop. Okay. What else? You all looked at this and you came to no conclusions whatsoever? None? Come on, let's get out there. Yeah.
The prediction of the annual temperature of 2020.
2020
Yeah.
predicted. I like this. Yep. Predicted average annual temp.
Yeah.
Yep.
46.164.
That's what you predict. Okay. Any others? Yeah. What do you think?
Like 1980 to 2010, whenever the temperature got like 47, 48, within the next year or two, would drop down to 10.
Temp would rise to 47, 48, then fall to what, 44, 45? Something like that? Yeah. It seems like it's oscillating. Now, the big question is, what is the general trend? Yeah, huh. Anyway, what other conclusions? Yeah, what do you think?
The average spring temperature goes up, but average forest temperature
Average what? The average
Fall.
average fall temp goes down. So even if the average temperature stays the same, does that mean that the climate is staying stable?
No.
No, it doesn't. This is a really challenging data set to look at. Any other conclusions? That's a really good observation. I like that. Any other ones? No other observations? Nothing? Yeah, it's okay if you don't. Yeah.
I was at from 1892 to 1932.
Yep.
Month of June.
Sure, yeah, that's specific. Yeah, okay.
Yep. And it was fairly consistent, and the difference between the averages that month were
No greater than what? Between any 2 months?
like the highest and the lowest.
Oh, looking at highest and lowest. Got it. Each month. Planetary extremes, that's an interesting thing to talk about. Where the coldest temperatures occur, where the hottest temperatures occur, where the driest, where the wettest points are. And we know what the coldest recorded temperature is on planet Earth and where it happened? Take a guess. Where's the coldest recorded temperature? Antarctica. It's like 1983. It was negative 89 degrees Celsius.
Celsius.
Was it Celsius? I think it was. I can't. Oh, I don't know if it was Celsius. No. Negative 90 degrees Celsius would be. No. Negative 89 degrees Fahrenheit. 89 degrees Fahrenheit. Hottest points. You know where the hottest points are? I don't remember exactly where. I know the driest though. They take a heat index, which is heat index is what, 2/3 the temperature plus 1/3 the humidity, something like that. It factors in humidity, right? Everyone understand what I mean by heat index? Yeah. Heat plus humidity is very dangerous. So the worst heat index, actually, United States. You know where it is?
I feel like I do know where this is.
It's in California. It's a valley.
Death Valley.
There we go. Death Valley. Death Valley. Got it.
I knew it
was yeah, the heat index was awful. I mean, Death Valley reaches temperatures of like well over 100, but then with significant humidity. That is insanely dangerous. Has anybody ever been in really, really hot, really, really humid temperatures before? Thailand. I was in Taiwan, Southeast Asia. I was there in July. Upwards of like 95, 100 degrees every single day, but the humidity was almost complete. It's unlike anything I've experienced. I've experienced 127 degree heat in Arizona before, but it was completely dry. Compared to this, that was nothing.
So it's like oppressive.
Totally oppressive. The only thing that was nice about it, completely consistent. Every day I knew when I walked outside, it was going to be boom! Okay, so the next question is, what did you learn about the process? What did you learn about the process?
You ready to
What's new? Yeah, yeah.
Not all of them. Every data.
Yeah, don't put in 999 data points, because that's what he did.
Oh no.
I rate them because like it's over.
He wanted to put them all in, but there's 1,500. The calculator only takes 999.
Oh no.
You win and lose.
So much time.
Goss, go. What do you got?
Um,
What'd you learn about the process?
you have to take into account data points that are left out and averages. Because as Alex pointed out,
Yep.
my graph has an extreme rise here.
Yep.
And that was because they had left out, they didn't record temperatures for a few months.
Yeah, there was like a period in
You need to take into account missing data points, as well as missing data points. What else do you need to take into account? Not only missing data points, what else?
outliers.
Yeah. Or not take into account outliers. Great book. Everybody should read it. Yes.
And in Microsoft Excel is a very good tool.
Excel is a great tool. Yes.
To draw functions, to draw scatter plot, to
You just need what? You need practice, right? Possibly. You could also Google Excel tutorial. Did you try that? To try it. We can try it a little bit. We don't have time right now, but maybe I'll try to work that in. That's legitimate, considering it is a skill you will certainly run into if you haven't already. Yes.
If you graph like every couple of years instead of every
Yeah.
year, you're probably going to get a better model.
Yeah. Try working with a regular interval. Try working with regular intervals of data. Got it? What else?
Pick a
Anything else?
specific thing you want to analyze.
Pick a very specific thing you want to analyze. It's really easy to what? It's easy to what it's easy to drown in the data, right?
Especially with that.
Yeah, especially with climate. What else? Anything? I'll just leave you with this. We're going to talk about modeling for some more, but just on your own, I highly recommend, if you're interested in thinking about things like this, there's a book called Freakonomics. If you haven't read it and you're interested in figuring out why things the way they are, it's fascinating. So they wrote Freakonomics and Super Freakonomics. That just came out a little while ago. 2 books, definitely worth reading.
the author I remember was the author of this document.
A critic, you mean? A what? Counter? What did you say?
Counselor.
Counselor, yeah. I don't remember. I don't remember their bios. One of them was a New York Magazine author, and the other guy was The Economist from Chicago. It's very interesting stuff. He looks at data sets, but not just climate or not just this. He looks at tons of things. It's answering really interesting questions. Like what?
Like how your first name affects your life.
How your first name affects your life.
Really?
Why did the crime rate drop in the 90s?
Yeah.
Wow, that's fascinating. When and why do teachers cheat? That was really interesting. Just because you have high-stakes testing doesn't mean it's a good thing, that kind of thing. It's very interesting stuff. Okay, so now let's move on here. What I'd like to do now is we're going to talk about rational functions. Let's talk about rational functions. You were supposed to come up with at least 2 questions about rational functions. At least 2 questions about rational functions. Can someone give me one specific question they came up with after looking at the presentation? Yeah, go, Shock.
I kind of wanted to know how, like, you use it for, like, a real life cases.
How do you use... What's the real-life application?
Yeah. Like, I was trying to think of a problem.
You need to do this in pass this class. Is that good? I understand your question. Other questions? You all have to come up with at least 2 each. Yes, Salmon.
How do you graph it if there aren't any intercepts?
How do you graph the function when there are no intercepts? That is a great question. What else? Yeah.
Why the domain is only about the denominator?
Why is the domain only about the denominator? Good question. I like that. What else? Other questions. Come on. No one else had... These are the only 3 questions the entire class could come up with? Was I that good at teaching this material online? That's where you say, yeah, of course it is, Mr. Seaman. Yeah.
Why there can only have one or 0 reference lines.
Why can there only be... x-axis this way?
Yeah.
Why can there only be one y-intercept?
Yeah.
Yeah. Why can only be one y-intercept? Okay.
Why can be a lot of, for
can there be many x-intercepts? Okay, what else? Other questions? Other questions? Any other questions come up? No other questions? None?
Is the point just to analyze it?
Our overall goal, once we learn all the steps, is going to be to, I'm going to give you one of these, and without a calculator, you're going to be able to you'll be able to graph by hand a pretty accurate representation. That's what we're going to aiming for. Yes, that's the goal. We are graphing by hand. I wrote that out, I think. Shh. Okay, so let's answer these questions. What's the real-life application? Certain data sets can be most accurately modeled by rational functions. And the second big reason is working with rational functions is a great way to learn about how functions behave in general. Just about everything that can happen to a rational function can happen to every other type of function. So essentially, if you can master graphing rational functions by hand, all the other ones are really easy. How do you graph the function when there are no intercepts? You must look at all the other data. And I gave you a hint. I think at the beginning of the presentation I said, if you get totally lost in your graphing a function, what can you always do? If I gave you a rational function right now and I said graph it by hand, I want it to be super accurate, you can't use a calculator, what would you do? Let's say you knew none of these steps. How would you make the graph? Plot points. So you're going to get a lot of data over here, and you're going to plot like one point, and because of that one point, you go, oh, I know that because that point is there, this point has to be up there, and you can fill in the rest. It falls into place. Sometimes you're going to need to just randomly pick some numbers and go with it. But do they have to cross axes? Yeah, so how do graph there are no intercepts? And the key thing is, where is it? You are not guaranteed to have any intercepts. Okay. Why is the domain only about the denominator? Can someone answer that question? Why is the domain only about the denominator? What are we trying to avoid?
Because we don't want to divide by. Oh, because
Avoiding divide by 0, right? Where's the only place that can be a problem? Yeah. Yeah, what about, is it okay if the numerator is 0? Yep. Why can there only be one y-intercept? Yeah, more than one y-intercept means what? Yeah. How many x-intercepts can you have? Yeah. Is it possible to write a function on your piece of paper like right now that has an infinite number of x-intercepts? Yeah, it is. It's possible. It's definitely possible. Okay, so we're going to practice these steps. First of all, what does DIS stand for?
Domain, intercept, symmetry.
Domain, intercepts, good, symmetry. So I have a present for all of you. R1. So R1 is right here. So if we want to start analyzing this function, our goal is to eventually graph this function, but we're going to do this in pieces. Step 1 is to do what? Find the domain. Can someone very concisely tell me how we're going to go about finding the domain? Raise your hand. Go ahead, Pang, yeah? Factor what out? Why? We're avoiding 0. Okay, I need you're touching on the complete parts. I need complete. I need string that together for me. Set what equal to 0? The denominator. There you go. You want to set the denominator equal to 0, and we want to know when it equals 0. Why? We want to avoid that. So if we're solving a quadratic, hopefully it's nicely what? Is it nicely factorable? Can someone tell me what the nicely factored form is? Yeah. So x is equal to 3. So what's the domain? Can someone tell me what the domain is? What's the domain? Anybody? Yeah, so x such that x does not equal negative 4 or 3. There's your domain. So there's the D. So now let's talk about intercepts. How many types of intercepts are there? X and Y. So the y-intercept is generally the easiest one if that's when what is true? When x is 0. When x is equal to 0 on this, what does y equal? 0. Because what's the top become? And what's the bottom become? No. Negative 12. If it was 0 on the bottom, we'd have a problem. 0 over negative 12 is? That's also, not only is that a y-intercept, that's also, it's not only a y-intercept, it's an x-intercept as well. Okay, so let's try the x-intercepts. How many could there be? An infinite number. So that's when y is 0. Now if we look at this original function, all rational functions are fractions. How do you make a fraction equal 0? Yeah, so we need to solve 3x squared minus 3x is equal to, and we always ask ourselves, is this nicely factorable? What can you factor out of both of these terms? Someone who hasn't spoken yet today. You've spoken. What?
3.
And? Yeah, so what's left? 1. So x is equal to 1. So we know that when x is 0, y is 0, and when x is 1, y is 0. Did we doubly find one of these? So do we have 2 intercepts? So now we have 2 intercepts. It's helpful. We know the domain. Here's the domain. That's going to be very helpful later. Next, we need to find the symmetry. How do we investigate symmetry? Plug in, set x equal to? Good. So we have R1 of negative x, and that's going to be 3 times negative x squared minus 3 times negative x all over negative x squared plus negative x minus 12. Well, that becomes 3x squared plus 3x all over x squared minus x minus 12. Now, what does that tell you? What is that not equal to? R1 of x, and it's also not equal to negative R1 of x. So what does this mean? Not, it's not even, it's not odd, it is neither. Now, does this tell you anything super useful? Not really, but it definitely tells you there's no symmetry, which is something. You're going to be gathering information, and then at the end you're going to take all that information and put it together. Any one of these facts doesn't really help you too much with the general picture, but once you get all of this information, you're going to put it together into one complete picture of what the rational function looks like. That's what we're going to do. The first part of your homework, hold on, the first part of your homework is do this on R2, R3, and R4. That's the first part of your homework. Please find the domain, intercepts, and symmetry for R2, R3, and R4. This is on the handout. Okay, you ready to do some fun stuff now? Always. So please do this on R2, R3, R4, and also complete the bean counting lab. Look over on the back. Turn your sheet over. There are questions you need to do. So that's what you're going to do that tonight. And the third thing is watch Rational Functions Part 2. Come to class with at least 2 questions about the video. Use the data you have to finish the lab. So if you only did like 6 or 7 generations, that's fine.
And you shared this